Hello and good morning or good afternoon, wherever you may be, and I trust you all are staying safe. I would like to give you a walk through our work on distributed dynamic channel allocation for a recent 6G INS subnetworks, essentially where we have an application in industrial automation. So here is an outline of the talk. I will start with an introduction, trying to introduce the whole concept of a 6G INS subnetworks. I would also highlight very briefly the KPIs and key requirements, as well as a touch on the initial designs. And then I would discuss the algorithms that we have actually investigated for dynamic allocation of radio resources. I would also show you some performance evaluation results. And finally, I would actually wrap up this talk. Okay, so the very first question is why 6G and why do we have the term INX subnetworks here? So this is a very recent idea that was actually conceived as a natural evolution from where we have with 5G networks and all that. We know that, of course, with 5G, we could essentially support a number of applications in the industry 4.0 framework. So, but here we are trying to look at it beyond that. Can we essentially try to actually target at removing the last cables in the industrial environment with wireless networks? For example, if we take the control of robotics arms and all that, traditionally we will have this being done over wired infrastructure. But what if we essentially try to replace these cablings with a wireless network? So such wireless network would, of course, need to have a very high determinism, both in a spatial and temporal basis, actually. So we actually conceive this to be something that cannot be supported by 5G, and as such, we would expect it to be a concept for what is generally known as beyond 5G. So such a network could also be used, for example, for intra-vehicular share communication, where, for example, we would like to replace the cabling in the CAN bus and all that with wired network. This could be, for example, very life critical applications like the engine suspension, the ABS and all that. Another very good application is intra-body network. For example, if we take a wireless heart pacemaker, so this would essentially require an extreme reliability to actually guarantee the safety of whoever is actually carrying the pacemaker. So these applications, which could potentially be life critical, we actually emphasize that we would have latency requirements below what is currently obtainable with 5G networks. So, for example, in most 5G applications, we have a delay limit of 1 millisecond. But given our knowledge about how networks actually evolve from 1G to 2G and all that, we say, okay, let's try to actually set a target of a factor of 10 for this future generation network. So, and as such, we would like to actually investigate the possibility of having wireless share communication that can actually support control loop with a loop cycle time of 100 nanoseconds, the reliability that is actually below 1E-6. Of course, we would also want to ensure that these requirements are met on a very high spatial temporal availability level. And for this, we actually define what we call the probability of loop failure, which essentially actually measures the probability that a particular shared communication loop would meet this latency and reliability requirement. So to support these extreme applications, we have an initial concept where we have looked at the key shared technology enablers for supporting these extreme reliability with super short cycle time, right? And then what we have looked at is to say, okay, given the type of applications that we would like to have these subnetworks used, we would expect that they are relatively short range, and as such, we could say be safe to say we would like to actually have low power networks, right? And then, of course, we actually assume that we have a periodic transmission with pre-allocation of radio resources, and we have efficient signal processing techniques for jitter control and all that. We would also need to have very short transmission interval. And of course, we hope that we could actually harvest both the frequency and what have you, the capacity by repeating the packets multiple times. This essentially actually gives us some advantage over and an improvement on the probability of transmission errors, right? And then for this work, we would basically actually consider a 30D mode. Of course, we could, in this work, we would actually concentrate on symmetric frame structures. Of course, this could also be adapted to cases where we need to have asymmetric transmission. We would also rely on the popular orthogonal frequency division multiplexing waveform or other enhancement of it. And of course, as we would actually expect, we would need to have relatively high subcarrier spacing. We hope to have at least above 240 kilohertz, right? So as part of our initial design and a recent article which was actually published in IEEE Assets on subnetwork idea, we have a frame structure like this. So essentially what we hope to do is to see, okay, we need to have this, the total frame duration here needs to be at least below the 100 nanoseconds cycle time target for the subnetworks. And what you can see here is we have this symmetric frame structure where the sensors to controller transmissions actually takes place for each device on pre-allocated time slots. And then each transmission is repeated blindly a number of times, and all these can then be chased combined at the receiver. Yes, so now I would, having introduced this, I would now discuss the algorithms that we have looked at to perform dynamic allocation of radio resources, with the bearing in mind that our main goal is to be able to actually guarantee the extreme reliability requirement for the subnetwork, right? So in terms of the system model, we have basically actually looked at a network of ES subnetworks having, say, n share subnetworks which are actually moving. So each network here actually moves, but we would actually assume there is no relative movement between the controllers and the devices within a given subnetwork. So the subnetwork moves, but they don't move relative to each other. So the task here is, given a limited amount of resources, how do we select a resource to actually transmit such that we would actually minimize both the interference that is actually generated to other subnetworks and the one and also ensure that our transmissions are not badly affected. So Yes. For us to be able to do this, we look at a case where we have a total bandwidth of B. We assume that this bandwidth is actually divided into a number of frequency channels, each with bandwidth BCH, right? In this case, we have 12 channels in total. Now, let's say we would like to actually repeat each transmission within each subnetwork thrice. Essentially, we can then say, okay, let's partition this entire bandwidth into a number of groups, such that each group has a number of channels that is at least equal to the number of repetitions that we would like to have. So in this case, we would have 4 groups. So the task now is that we would assume that we can then restrict each subnetwork to transmit within a group at a given time, and only actually switches to another group when the condition on the currently occupied group becomes bad or becomes worse than expected to meet the requirement. So now, talking about algorithms to be able to do this selection. So what we have done here is to actually assume that each subnetwork actually has a controller, and the controller can perform spectrum sensing to determine the state of all the available groups, and as such has some information to be able to select a channel to actually transmit, such that at least the worst case SINR within the subnetwork is at least below the SINR required to meet the target outage probability. We also assume that each controller, of course, has a knowledge of the SINR limit, which can easily be calculated from the target outage probability and all that. So the task now is we would like to have an algorithm which continuously monitors the entire spectrum, and based on this information, we can then try to actually select where to transmit on. So for this, we have looked at a number of algorithms. We look at a class that we call the epsilon greedy selection algorithm, where basically when you keep tracking your SINR, the worst case SINR within your subnetwork, and then when that becomes bad, you initiate a channel switching process, and then you would then need to select a new channel to transmit on. And how you do this is by selecting either greedily with some probability or randomly with 1 minus that probability. Right. The other algorithm we have looked at is what we call the minimum SINR guarantee. So essentially what we are doing with this is that if we go completely greedy in the epsilon greedy case, where we set epsilon equals to 1, then we would actually run the risk that multiple subnetworks actually jump into the same relatively good group at the same time, and this would cause problems for the transmission and all that. To minimize this, it could be a reasonable idea to basically just actually select a channel group that is only good enough to meet my requirement, and as such, I don't act too greedily, right? So here, basically, you track your SINR. If it's below the threshold, you switch a band. Essentially, what you try to do is to select the worst channel that meets your requirement. And if there is none available meeting the SINR limit, you would just actually select the best channel group. Now, and finally, we also look at another distributed allocation algorithm, which we call the nearest neighbor conflict avoidance. Essentially, what this does is to actually say, okay, in the other algorithms, we have basically relied on the total or aggregate interference interference per measurement on each of the channels. What if we now make a new assumption that each subnetwork actually has the capability of monitoring and identifying the channel groups that is actually occupied by at least k minus 1 nearest neighbors, where k is the number of groups that we have, right? If we do this, then the selection is basically done by just avoiding the channel that is occupied by your immediate neighbors. And if there are multiples that are not in use, you just choose randomly from the available list. As a baseline for comparing the distributed algorithms, we have also looked at a centralized graph coloring. Essentially, what we do here is at every transmission time instant, we make an interference graph or distance matrix graph kind of. And then with this, we can then apply some graph coloring algorithm. Here we have chosen to use the greedy graph coloring algorithm to assign the channel groups to each subnetwork. So here is just a summary of the algorithms. Now we would move into evaluating the performance of the algorithms and see how they actually compare to each other. So before we go into that, here basically we have actually just shown how we actually calculate the outage probability. Here we have the SINR, which is calculated here. I would like to actually point out that this term is basically due to the fact that we have actually assumed that the subnetworks are completely uncoordinated, and as such, we could have this mutual interference between uplink transmissions and downlink transmission. And the first term here is basically the traditional term that we would have. Essentially, we have an additional interference in cases where we don't have perfect synchronization among shared subnetworks. And what we have on the left is essentially an outage probability versus SINR map, assuming a subcarrier spacing of 480 kilohertz and a 20 megahertz fading block size. So we would use the configurations with 2 RS in our evaluation subsequently. For the results to actually come, we have a deployment with 16 shared subnetworks, each subnetwork having 18 shared sensor actuator pairs. We have a total of 12 channels with a bandwidth per channel from 40 megahertz to 320 megahertz. And then we will actually partition this into a number of groups. And depending on the number of partitions or groups that we have, we also scale the number of repetitions accordingly. Each subnetwork actually moves at a constant speed of 2 meters per second in a 30 by 30 meter rectangular area. Now, for the path loss model and shadowing, we have basically used this to actually calculate the received shape power, where we have the path loss component and the shadowing here. To generate the shadowing, we have used the Gaussian random feed-based model, where we basically make maps and then update the maps at some regular interval, and based on the map, we can then compute the link shadowing using the following expression here. Right. Now, the very first question that we try to ask is, what should we do? Should we actually have more repetitions, or we don't have at all and just allow all subnetworks to actually transmit on any of the bands within the entire number of channels that we have? Or should we divide them into a number of groups and also scale the number of repetitions accordingly? And what we see is that if we don't repeat at all, then we get something that is relatively bad compared to a case where we have 6 groups and then we repeat twice. So the transmission from either a sensor to a controller or from a controller to an actuator is repeated twice in that case. So that seems to be an optimal configuration for the scenario we have looked at. So for this, we would then actually rely on this configuration to do a comparative analysis. I would like to point out here that the plot being shown here is actually obtained using the baseline centralized graph coloring algorithm. So here we basically try to actually compare the algorithms and benchmark that with the centralized graph coloring, as well as a case where we don't do any grouping. So all subnetworks can basically use any of the frequency channels, right? And what we see essentially is that the nearest neighbor conflict avoidance algorithm performs very closely to the centralized baseline. This is actually expected given the amount of information that is required. Here we have actually assumed that each subnetwork is explicitly able to determine or identify the channels occupied by its nearest neighbors, and as such, this can dramatically result in a drastic reduction in the interference footprint. We see also that, of course, the minimum SINR guarantee actually performs better than the completely greedy algorithm, which is the red line here. So it seems like depending on the scheme and the amount of information, we can actually scale the bandwidth required by order of magnitude. For example, if we compare the NNCA with the no grouping case, we would see that we have a more than twice reduction in the amount of bandwidth required to support a PLF limit of 1E minus 6. So the plot we have on the side here is basically trying to actually compare the switching overhead, because essentially what we would like to actually have, we have an algorithm that is actually performing well, and it's also not requiring additional resources to actually enable channel switching. So this could be, for example, how to actually communicate switching decisions to devices within a subnetwork and all that, right? And the lower the frequency of this, the better. And as a metric for evaluating this, we have basically used the channel switching frequency, so which basically actually takes the percentage of the number of time instance where channel switching actually occurs to the total time instance that we have. What we see is among all the distributed algorithm, the NNCA seems to have the lowest switching overhead. So what this means is that we can get a very good performance at a relatively low overhead, given that we have accurate identification information about shared subnetworks. This identification may actually in practice be a very difficult process, but our current work is also looking at aspects that relates to a protocol for performing this identification and all that. So finally, we made an estimate of the bandwidth requirements to actually support such extreme requirements, a PLF of 1E minus 4 or 1E minus 6, for example. And what we can see, which actually agrees majorly with our earlier studies, is that we need gigahertz of bandwidth for us to be able to support this. But what is worth of noting here is that we compare a case where we don't do anything to the case where we have either the NNCA or the centralized graph coloring algorithm. We can see that the bandwidth required, even though it's still relatively high, is a decrease of more than half, right? So for example, from here, we would go from above 4 gigahertz to below 2 gigahertz, so which is a very dramatic, a very drastic improvement given how expensive bandwidth resources are. So to actually wrap up this talk, we have actually presented a number of algorithms for performing distributed allocation of radio resources in a recent 6G inert shared subnetworks, which are basically autonomous cells or short-range cells, which are expected to be used either for industrial control to control, robotics arm for intravehicular applications, intra-avionics, or on-body networks. We have looked at simple schemes relying on measurement of the SINR and the interference power to enable dynamic allocation of resources. And our studies and evaluation results have shown great potential for improving the performance, and most importantly, decreasing the bandwidth requirement to support this extreme futuristic requirement. Our current research effort is actually looking at how we use machine learning methods. So we actually introduce some kind of intelligence into this subnetwork, and also evaluate how much gain do we get by having this intelligent subnetworks. We would be available to actually take your questions and all that. Thank you very much for listening.